Hello guys, how are you doing? Nice to see you.
Good. You?
Okay, yeah, not bad. Okay, so I guess today we should not waste time and go for our discussion, because last time we did almost nothing and we still have to cover quite a big topic during this week. So I change the camera and just short recall what we were doing. We were trying to derive the equation of simple harmonic oscillation. To be more particular, describe the position of block attached to a spring, assuming there is massless spring and no friction. So describe the position x of the block as a function of time. And we know that such oscillations, they just like follow the definition of simple harmonic motion. Okay, so the spring force is equal to minus kx. So I just write here a bunch of initial equations which we use in this derivation. And then we can connect it to the linear acceleration. Minus kx is equal to ma, according to second law of motion. And from here, acceleration is minus km divided by m times x. So this is the condition of simple harmonic motion. As I mentioned before, acceleration is linearly proportional to coordinate x and goes oriented in the opposite direction from the displacement because of this minus. So this is the required condition to claim that the motion we are dealing with is a simple harmonic motion. So acceleration is the first derivative of velocity, dv over dt, and second derivative of the coordinate of displacement. So based on this, we can write a differential equation where x dt squared equal to minus k m x. So here, instead of a, we put second derivative of displacement x, and we get second order linear differential equation plus k over m x equal to 0. So now our task is to find function x t. Find the dependence of displacement or position of the block as a function of time. So the way how this specific type of differential equations, second order linear differential equations, are solved, you need to assume that, for instance, lambda stands for first derivative of the function over independent derivative over independent variable, and then we write a so-called characteristic equation. So I do want to give you detailed solution of this differential equation, so you really understand step by step why final equation of simple harmonic motion is this or not different from that, which is given by the textbook. So you will learn, of course, in mathematics course more in details how to solve differential equations. But here I show you one example of this particular type of differential equations. And quite often we deal with these types of second order linear differential equations, second order because we have second derivative involved in this differential equations. So we write characteristic equation, which is lambda square. So lambda stands for first derivative, so lambda square stands for second derivative, plus k divided by m. So this coefficient next to the function, we don't write here function in the characteristic equation, it's equal to 0. So this is nothing else as like simple quadratic equation. So how do we solve quadratic equations? We look for discriminant, and this is like standard formula b minus 4ac. So here b is equal to 0. We don't have lambda involved in this quadratic equation. So then we have minus 4. A is unity, and C is k divided by m. So our discriminant will be minus 4k divided by m. So what is special about this discriminant?
It's imaginary.
I mean, the discriminant itself is negative, and solution of this quadratic equation, you are right, it will be imaginary. It will be some conjugated imaginary number. So let's go and get this answer, this solution. So lambda 1, 2, we will get two solutions, of course, will be equal. So again, standard equation to be consistent, minus b plus minus square root of discriminant divided by 2a. So what it will be? So it will be, I mean, let's write it 0, b is 0 plus minus square root of minus 4km divided by 2, because a is unity. Then let us rearrange this a bit. So 4 we can take out from the square root, so it will be 2. Then minus, we also can take out from the root. It will be square root of minus 1 times square root of k divided by m. And this is divided by 2. 2 and 2 we cancel out, and this square root of minus 1 is denoted as I in complex numbers. So sorry, here I forgot to put plus minus. And we will end up with plus minus I times square root k divided by m. So this is a solution of our characteristic equation. And if, and it's another step in the process of solving this type of second order linear differential equation, if the solution of the characteristic equation is given as in the form of conjugated imaginary numbers, like plus minus I times k over m in our case here. So if we have imaginary roots for the characteristic equation, then the solution of the differential equations is given in the following form. So this is form of solution for differential equation. Actually, it's our x as a function of t. That's what we are looking for. Should be in the form like this. So it should be constant 1, like C1, times cosinus square root of k divided by m. It's actually based on our solution of characteristic equation, times t plus C2 sinus square root of k divided by m times t. So don't ask me why this is the case. It's just pure mathematics. You have what you need to do when solving this type of any type of differential equations. You look at the differential equation and you need to identify what type this differential equation is. And then for each type of differential equations, there are very clearly defined rules and step-by-step rules how to solve them. So in particular, for this type of differential equation, we need to solve characteristic equation, write a characteristic equation, solve it, look what kind of solution we get for characteristic equation. Based on that type of solution we get for characteristic equation, we finally get the form of function which will be the answer to our differential equation. So this is the step-by-step approach to solve it. However, it's not finished yet. So what we need to define these constants, C1 and C2. And for this, in order to do that, we need to define some boundary conditions. So as you may remember from previous discussion, I was drawing this like spring with the block attached to it. So we first stretch the spring to the distance of x equal to, let's say, capital A, x equal to capital A, and then let it go. And we start counting time from this moment when we let the spring move backwards. So at t equals 0, our displacement, the coordinate of the block, is equal to A, capital A. So now, based on this condition, we will proceed further with the determination of some of these two constants. So this is our first boundary condition. And before we proceed, actually, let us make some substitution. It will be more convenient for us. Let's assume that square root of k divided by m is equal to omega. Omega is angular velocity, and it makes sense because you see we have cosinus square root times t. So cosinus should be taken from some angle, and product of angular velocity to time will actually give us the angle. That's why we make this replacement. Then it will be easier to write all these equations again and again. Okay, so now let us rewrite this with omega. C1 times cosinus omega t plus C2 sinus omega t. And now we take into account this boundary condition. So at t equals 0, our displacement should be equal to A. So based on this boundary condition, we will get A is equal to C1 cosinus here we will have 0 because t is 0 plus C2 sinus 0. So sinus 0 is equal to 0 and cosinus 0 is equal to 1. So we will get from here that our constant C1 is equal to A. Okay, so we, with this first boundary condition, define the first constant. Now we need to define the second constant. We need one more boundary condition. Do you have any ideas what kind of boundary condition we can consider? What at t equals 0 we know about the block besides that its displacement is equal to A capital? What are the parameters we need to describe the motion of a body? Its initial position, and then what else? Another important parameter is its velocity and of course acceleration. But let's consider velocity. What do we know about our block at t, like time equals 0? So it's in extreme point, stretched to extreme point, displacement is A, but the block doesn't move. So it starts moving only at t equals 0 and increases its velocity. At t equals 0, velocity is equal to 0. That's why we can consider this fact as a second boundary condition. And in this case, we claim that v is equal to dx over dt, and this is equal to 0. So let us take first derivative over t from our equation for x as a function of t and set it to 0. That should help us to calculate the value for the second constant, C2. So we have the function, it's here. Let's take first derivative. So maybe here we just write for reference that derivative of cosine x is equal to minus sine x, and derivative of sine x is equal to cosine x. Okay, now let's take the derivative. dx over dt is equal. So we have c1 times cosine omega t. So this is actually a complex function because we have cosine and then omega t in the argument, some linear function. So that will be c1 times minus sinus omega t is derivative of cosinus omega t, and then times omega. It's derivative of the argument of the cosine. Plus, we have here similar picture. It will be C2 times, now we have positive cosine omega, cosine omega t, and times omega. Okay, so this is equal to 0 at t equal to 0. So let us put t equal to 0. Then here we will have sinus of 0, and here will be cosine of 0. So sinus of 0 is 0. This is true at t equal to 0. And cosinus of 0 will be unity. So we can rewrite this. This part will be equal to 0. And then we end up with only this part. And we see that this part is equal to 0. That means that since omega, angular velocity, is not equal to 0 because it's equal to square root of k divided by m, and these are constants and they are not equal to 0. So this part will be equal to 0 only when C2 is equal to 0. So this is the way how we use second boundary condition, that our velocity at t equal to 0 is equal to 0. Then we figure out that C2, constant C2, is also equal to 0. And now, based on determined values for our constant C1 and C2, and taking into account the general function for the solution of our differential equation, we can write the final equation for the x as a function of t, assuming our given boundary conditions. X as a function of t is equal to C1. C1 is equal to A times cosinus omega t. And that's all because we have C2 is equal to 0, then that's why C2 sinus omega t is also equal to 0. So this is the solution of our differential equation, assuming given boundary conditions. When we consider that t equal to 0 is when we like stretch the spring to its maximum, displacement equal to A, capital A. Okay, let us write it on the new slide. So x is equal to A times cosinus omega t. So in order to be even more general and have a chance to consider harmonic oscillations at any initial setting t equals 0 at any position x, because it's sometimes we don't assume like start monitoring and calculating the displacement as a function of time exactly at the position x equal to capital A. It could be already that we start calculating the motion after some time when, for instance, this block is moving through the x equals 0. So there is some phase shift between initial condition and current time when we start calculating. That's why, in order to take into account this difference, it's so-called phase shift, general solution will look like this. We have cosine omega t plus phi. And phi, this is this initial phase shift between time in oscillation. So this parameter A, which stands in front of cosines, is called amplitude of the oscillation, which means the maximum displacement of the block. Omega, as I mentioned before, it's angular velocity, and it is equal to square root of k divided by m. We did this substitution previously. And phi is the phase shift. Okay, so now we have the solution for the simple harmonic oscillation, the quantitative solution for this specific case, and let us discuss some other parameters which are related to this type of repeatable motion. So first of all, since we know the position as a function of time, it makes sense to consider velocity and acceleration as a function of time, which corresponds to this simple harmonic motion. So for this purpose, we take derivatives. For velocity, it is first derivative, dx over dt. This is equal to minus, let's do it step by step. A times minus sinus omega t plus p, then times omega. So this is the derivative, and we can write that it's minus a times omega sinus omega t plus phi. So this is the equation which describes velocity of the body, which performs some simple harmonic motion. And now we determine the acceleration. This is the second derivative of position, d squared x over dt squared. So here we need to take derivative already from this function of, it will be equal to make it clear, dv over dt. So now we take derivative of the velocity over time. So what will we get? It will be minus a omega, these are constants. Then derivative of sinus, it's cosine. omega t plus phi, and again times omega. It's derivative of this argument over t. So we end up with minus a omega squared cosine omega t plus phi. Okay, so this is our acceleration. And we can, based on these equations for the velocity and acceleration, define the maximum values, like so-called amplitude values for the velocity and acceleration. And this will be V maximum. How do you think, what will be the maximum velocity?
At t divided by 4, like period by 4.
Oh, can you repeat, please?
You're asking the time when it will be maximum?
No, not time, like...
minus amplitude multiplied by omega.
Yeah, so let's consider that we have just absolute value. So it will be, you're right, it will be a times omega. So this is what we have in front of the sinus. And for acceleration, like maximum acceleration, it will be also according to this logic, like number in front of the cosinus will be a times omega squared. And assuming that, so this omega, it kind of doesn't tell us by itself very much, because it can be kind of any number, but we know that this omega is defined by the properties of the system. So omega is equal to spring constant divided by n. So then we can already, based on these equations, define, based on these equations and properties of the system, define what will be the maximum velocity and acceleration. That will be a, like maximum displacement amplitude, times square root of a divided by m. And the same will be here, a, but without square root, because here is omega square. In second power, it will be a times k divided by m. So you see, based on properties of the system, in particular, spring constant of the spring, mass of the block, and maximum displacement, we already can define this maximum values for which block will reach in this simple harmonic motion based on given conditions. Okay, so now we need to proceed further in the description of this, of parameters related to this simple harmonic motion. And let us introduce the period t. So period of the of motion is the time interval during the particle or the body goes through the cycle, the whole cycle. So it repeats whole cycle over and over by coming back to its initial position, and the time interval which is required for the body to finish one cycle is the period of the oscillation. And by definition, as I just mentioned, that the body comes back to the same position after time interval, which is equal to capital T, which is period. So that means that the phase of oscillation, like phase of oscillation, is this argument in sinus or cosinus, should be the same before, like, and after time interval equal to t. So we can write it in the following way. Omega times t plus period plus phi phase shift is equal to omega t plus phi. And the, sorry, it's not equal because it's not position, it is phase. So the difference between phases, so it's minus here. The difference between these phases will be equal to 2 pi. So means that difference between the phase at t plus capital T plus period minus phase at omega t plus phi is equal to 2 pi, and 2 pi means it made one whole cycle. So from here, we can write that omega t, if we open the parentheses, is equal to 2 pi. And we get the definition of period t in terms of angular velocity, and it's equal to 2 pi divided by omega. If we assume that omega is equal to square root to k divided by m, we can write that t is equal to 2 pi square root of m divided by k, because omega is in the denominator here. So that's another important formula which gives you the period of harmonic motion of this block attached to a spring based on the parameters of the block, like mass of the block and strands of the spring. There is another parameter which is frequency, and frequency is how many full cycles, like full oscillations, are done per 1 second. Means that frequency is defined as 1 divided by t, 1 second divided by a period of the oscillation. And then it will be equal to 1 over 2 pi square root of k divided by m. So period and frequency of oscillations are important parameters which describe simple harmonic motion and can be calculated by using these equations, which are based on the properties of the system under investigation, which is mass of the block and spring constant. Okay, so let's change the slide and maybe we continue further, because there are other parameters of this motion which should be considered. So in particular, energy of the simple harmonic oscillator, like simple harmonic motion. So let us first consider the kinetic energy of simple harmonic motion as a function of time. So kinetic energy, K, is equal to 1 over 2 times m times v squared. So we know that v, velocity of the simple harmonic motion, we derived it on the previous slide, if I'm not mistaken, it was minus omega a times sinus omega t plus phi. So now we can substitute this omega, this equation instead of omega, instead of v in the equation for the kinetic energy, and we will get kinetic energy for simple harmonic motion will be 1 divided by 2 times m, then v in second power. It will be, so minus will cancel out, and we will have omega square a square sinus square omega t plus phi. So this is the equation for the kinetic energy as a function of time. Let us go for potential energy. Potential energy of the spring, we know how it calculated. It is 1 over 2 times kx squared. Okay, so x, we also have equation for x as a function of t. It's a times cosine omega t plus phi. It's actually a solution of our differential equation, assuming the given boundary conditions. So based on this, we can also write that it will be 1 over 2 k a square cosine square omega t plus phi. Good. So now, in order to proceed further, we need to do some changes, like rewrite a bit expression for the kinetic energy, assuming that omega is equal to square root of k divided by m. So let's substitute this instead of omega here. So let's write kinetic energy is equal to 1 over 2 times m times k divided by m a square sinus square omega t plus phi. Okay, so m and m we cancel out, and it will be 1 over 2 k a square sinus square omega t plus phi. Okay, now we see that the constants before cosine and sinus for potential energy and kinetic energy are the same. So we can factor it out, and then when we calculate the total mechanical energy of the simple harmonic motion, so total mechanical energy is equal to the sum of kinetic energy plus potential energy. And this, okay, sorry about that. Total potential energy is equal to the sum of kinetic and potential energy. And this is equal to 1 over 2k a squared. So we factor this out because this constant is the same for both types of energy. Will be cosine square omega t plus p plus sinus square omega t plus p. So this, from the course of trigonometry, you should know that this is equal to unity, and it means that total mechanical energy of simple harmonic oscillation is a constant of simple harmonic motion and doesn't depend on time. 1 over 2k a squared. So it's actually equal to the maximum potential energy which was provided to the the spring gained. So when we stretch our spring to this maximum displacement A, and we see from this derivation that the sum of kinetic and potential energy at any given time of simple harmonic oscillation is a constant, and it's equal to the maximum potential energy of the spring. And this is another important feature of this simple harmonic motion. Of course, this is true only in the isolated system when we don't have dissipation of energy because of friction. So if friction is there, so I hope we will have time to consider oscillations with some friction. So you will see that, of course, total mechanical energy decreases. But for this particular case, when we consider frictionless simple harmonic motion, the sum of kinetic and potential energy, total mechanical energy, is a constant of simple harmonic motion. So this can be used actually to determine velocity at any given displacement x. So let us consider this case when we need to determine velocity at a given position x. Then we don't need actually even time. We can use this energy total mechanical equation for the total mechanical energy of a simple harmonic motion. So we know that total mechanical energy is equal to 1 over 2 mv squared plus 1 over 2 kx squared. So at each x we will have corresponding value for v, and this is equal, as we already derived on the previous slide, 1 over 2 ka squared. So this is constant. From here we can determine v at each position at each value of x. So for this purpose, first of all, we can cancel out this 1 over 2, and then move to the right this kx squared, and eventually we get the following equation. V as a function of x is equal to plus so it will be equal to ka squared plus minus, not plus, sorry, kx squared. So factor this out, k will be a squared minus x.
Professor.
Yeah?
I think we forgot about the mass.
Oh, yeah. You are right. So
and square root.
Exactly. I kind of wanted to go one step ahead, but then decided in last moment to do it step by step. So you are right. Yeah. mv squared like this. So now it is correct. Yeah. And from here, v as a function of x will be equal to square root of k divided by m times a squared minus x squared. And another thing, we should put also here plus minus, because this value will be of velocity, it will reach this value twice for the same location, because it can move from the left to the right, and then it comes back from the right to the left. And at the same position, x, it will have the same velocity by magnitude, but it will be in different directions. So since we have a single one-dimensional case, and we define the direction by the sign, we should put here plus minus square root, because it can be either positive or negative at the same x, depends at which phase our oscillation is. So taking into account that omega is equal to square root of k divided by m, we can write here that it will be equal plus minus omega square root of a second power minus x second power. Okay, so this is an equation which gives us the relationship between velocity at any position x, and this is what we can easily get from the total mechanical, from the concept of total mechanical energy of simple harmonic motion, which is equal to a constant 1 over 2 divided 1 over 2 times ka squared. So you can double check, for instance, this equation for our boundary conditions. Let's say at x equal to a, we know that v is equal to 0. And if we substitute x to our equation, x equal to a, so instead of a, we will see that it will be a squared minus a squared, so it will be v will be equal to 0. And also, if we consider x equal to 0, this equation, like velocity at 0x, will be plus minus omega square root of a second power, will be plus minus omega a. And this is nothing else as the maximum velocity which we defined earlier. So this equation works and can be kind of handy to calculate some like velocity at different position for simple harmonic motion without involving time. Okay, guys, so I see we overshoot it a bit with time, but it's good because we kind of finished with the quantitative description of simple harmonic motion, and that is very important part of this chapter. Okay, thank you very much for attention.
Excuse me, Professor.
Yes, you're welcome.
One question. If we like implicitly differentiate the second line equation, like mv squared is equal ka squared minus kx squared, can we get the similar function of acceleration without time involved?
Yes.
So it would be a proper function.
Yeah, I mean, you can, I mean, you need to differentiate it over time. So you cannot differentiate it from like Vx over like dV over dx. So you need to differentiate then V as a function of time, like dV over dt, and then dx over dt, and then it will be kind of complicated. So what you can do, for instance, with this equation, since here is equation of V as a function of x, you can take first derivative, set it of dv over dx, set it to 0, and then you will have an option to find maximum velocity, like extreme point of this function in a different way than using this equation, as I did it.
Okay, thank you.
You're welcome. But in order to go from velocity to acceleration, you need to take derivative of velocity over time, not over x. So you cannot proceed further. Okay, thank you for your attention and have a good evening.
You too, thank you, goodbye.